because it'll make life a little easier. Okay. All right. So everybody was good with the structure for carbon dioxide, right? Okay. Funny enough, has anybody ever tried to Google a molecule, a drawing of carbon dioxide recently? So I was just trying to snatch an easy carbon dioxide so I could throw it on here. This is the most freaking difficult thing. I'm not joking. All the top search results give it as bent. Like, what's going on? Is this AI? I don't know. It's just bizarre. So obviously not bent. That's crazy. And that's very experimentally observable, right? Okay, so what do we do for the symmetry? What symmetry is that? Mm-hmm.
It is 1C2.
Okay.
No perpendicular.
Does it just have a C2?
Yes.
It's because linear is D.
Yeah, if it's linear, then you always have infinite planes. Because they're the rotation with the axis through the entire molecule, right? Yeah. And so that always has to be one of the infinities. Yeah. So it has a C infinity, yeah. And then we come over here. Can you invert?
Yes.
Yeah, you can, right? Because two oxygens, right? If you'd had like a carbon monoxide, you couldn't invert, could you? Okay. And that would be where you separate. Okay, that making sense so far? Fantastic. We don't need the rest of the table, but I went in and split it up just so you guys would have it in case somebody went all the way down on this. So this is actually the D infinite H right here that corresponds to that. That's the character table here. Everybody okay with that so far? Okay. So which ones are Raman active again? Mm-hmm. Which ones are IR active?
Linear ones.
Okay, yep. And specifically, anybody know what that symbol is?
The summation you're talking
No, the symbol. The Greek symbol. That's capital sigma. Okay, that's capital delta. Okay. Okay, anyways. Yeah, so capital sigma, pi, delta. That will actually become important later. All right, so we have now which one of these would be infrared active, which one would be Raman active, right? Is everybody okay with that so far? Notice in this case, they don't line up. Mm-hmm.
The only IR active ones with the Z and then like parentheses XY, right?
Mm-hmm. You got it. And so those are the only two that you actually have to deal with in this problem because it just asked you IR active, right? But if you were trying to just figure out all Raman and infrared active ones, you would have to deal with these ones, right? Raman, infrared, and then those would be rotational. Okay. Okay. Now, this right here is actually Hertzberg. This is actually how you can easily figure out the number of infrared and Raman active bands based on that molecule, right? Okay. And so how many atoms do we have in this molecule? 3, exactly. And so we need to go ahead and, oh shoot, I cut the wrong part of the table, didn't I? No, I had to have it. Okay, I just can't see it. Can you guys see that any better than me? Not much. All right, that's great. Guess I should have blown that up more. Okay, so did everybody use the Hertzberg table whenever you're doing this? No? How did you guys go from, what did you do next after you figured out the symmetry table?
I'm kind of confused by the symmetry table because shouldn't there be 3 infrared like nodes?
No. These are irreducible representations. They are not modes. They're not bands. You could have 100 of them in this one right here. If you had a large enough molecule, you'd have 100 of them here, 300 here, whatever, right? Like that. This tells you nothing about the number of bands or modes that are in each of these irreducible symmetry representations.
Okay.
What this tells you is that it has these sets of transformations, okay? And then it has, by the way, it's the same as right here. It then has, these are the rotational ones that affect the rotations in the XYZ. These ones affect the translations in the XYZ and are also infrared active because of that. Okay? And then these ones are Raman active because they affect the orbitals according to these quadratic formulas. Okay. And so that's all you need from this one right here, is that these are Raman active right here, here, and here, right? This is infrared active, and this is infrared active. This tells you nothing about the number of vibrations, though. Okay? Okay. All right. So to do the number of vibrations, you would actually have to do it two ways. So there's two ways to do this. Okay. One of them requires you to do matrix calculations. And that's the one your book actually takes you through, the textbook for this course. And that is to take each of the different types of vibrations, write them out, and see how they transform in each of these transformations. And then you'd have to multiply them by the orthogonal, and that would actually give you which bands lined up with this. Okay? The alternative method is to use a simple linear problem that's in Hertzberg. And that's this right here, right? Okay, I'm going to go ahead and pop this down real quick so I can rearrange these. Because I don't know about you guys, but I couldn't actually read that. All right, so that's this right here. Can you guys read that better? Okay. All right, so this is the formula tables from Hertzberg. Okay, so if you go on page about 140-ish, has all these tables. These are the same character tables, right? Same point group symmetries, but they've solved these down to give you the number of vibrational modes in each of these irreducible representations. See, those are the same irreducible representations as is here. Okay. Notice that most of these modes have such high symmetry that you actually have no vibrations in them. You just can't get a vibration in those. Okay. And so this is all those extra modes that are here that you just don't need to deal with for this purpose. Okay. And so what you're going to do here is you're going to go through, this is the footnote at the bottom of the table, and you're going to find what atoms lie on what symmetry elements. Okay? So again, this right here is the number of atoms. This is what you want to solve first, so you know you have the correct numbers for each of these things. Okay? In this case, we have 3 atoms. So there's kind of only 2 ways to get this, isn't there? Okay, there's on every symmetry element and on none of the symmetry elements, right? Okay. So what we're going to do here is, again, if we look at M0 and M infinity, right? So M infinity is what? So if we read down here, Which one's M infinity? Okay, well, what's the only one that has numbers? M number. Can you guys read this right here?
Sets of nuclei on a fold.
Yeah, two-fold, three-fold, four-fold axis, right? Yeah. And so an M infinity would be infinite,
And it folds.
yeah, axis. Yeah. And so what ones are on that, but not on any other element of symmetry? So we have CO2, right? Okay. So what elements of symmetry would we have? Well, we can look up here, can't we? Okay, so we have our rotational axis, right? And then we have the plane of symmetry. That would be opposite to that, right? Okay. And that would be between, on the carbon, wouldn't it? Yeah. And so that central carbon that has a two-fold axis that can rotate around. Can everybody see that? Like a little propeller, right? Okay. And an infinite axis going through the entire molecule. And then a plane of symmetry right here, right? Okay. Okay, so the oxygens are going to be sets of nuclei on this, right? The M infinity, but nothing else, right? And then the carbon is going to be on everything, isn't it? Can you guys see that? Do you guys have your kits? You can't see it? Okay. If you can't see it, grab your kit, make your molecules. Try this real quick.
What is it? What are you talking about fold? What's the word fold? in that?
Axis. It's number of times you can rotate around the axis. Fold. Fold around the axis. So it's just the numerator, like the Cn. So C2 would be twofold. C3, threefold.
Oh, okay.
Yeah. C infinity, infinite fold. Yeah. Okay. All right. So again, we're doing C2. We got our character table, and so does everybody see that the carbon has to be the one on every element of symmetry? And then the oxygens are the sets of nuclei that are only on the axis, right?
So it's not just talking about the principal axis, 'cause the principal axis would be this and through all
Yep,
three atoms.
that would be the principal axis.
Okay.
But it has to be sets of nuclei not on any other element of symmetry.
So it's talking about this.
Yeah, there's a twofold axis that goes to the carbon, right?
Okay.
So the carbon doesn't count for this one. So this M infinity can't be the carbon, can it? Yeah, it's the oxygens. Okay. Okay, and then M0, that's going to be on everything, right? All elements of symmetry. And that excludes the oxygens, doesn't it? Because the oxygens are not on the C2, they're not on the plane of symmetry, are they? The reflection. Everybody okay with that? Okay. Okay, so we always double check. So we have a 1 here, we have a 1 here. 2 times 1, 2, 3. That's the number of atoms, isn't it? Okay. Okay, so then we plug these numbers in. Again, we only have to do the ones, well, we can do them all real quick if you want. So we would plug in 1 here. So there's one mode that's active in this one. Okay. There's 1 plus 1 minus 1. So that's one mode that's active in this one, right? That's 0. We don't have to worry about it, do we? Okay. This one here is 1 minus 1, and so it's 0 again. This one here is 1 plus 1 minus 1 again, so it's just one mode, isn't it? Okay. Okay, and that's 1, 0. Mm-hmm.
Why would the infinity 2? Because there's 2 oxygens that's not getting on the axis.
Okay, so that is the number of sets of nuclei.
Oh,
So the oxygens are one set of nuclei, right?
okay.
Because they're the same nucleus. Yeah. By the way, an isotopically labeled sample would actually have a slightly different answer to these things. Yeah. And so you can actually generate different forms. Okay. Anybody have any other questions here? Okay. Everybody got how you get the numbers there? Okay, so once you have those numbers, you would go back to this table here, and that's going to tell you your number of infrared, your number of Raman active, right? Okay. So for example, we double check this one. So that's the U plus. That's right there. So there's one mode active there, isn't there? Okay. Everybody okay with that?
I'm sorry, can you say that one more time?
We look here, this is the U plus here. So this was the U plus, that's infrared active. So there's one infrared active mode, that's that irreducible representation, right?
Okay.
And then you'd go here, and you'd look that up. There's another mode there, okay? Okay, and so you're going to see how many infrared bands, by the way.
And that one too.
Yeah, that would actually be 2. Okay? Anybody know why the answer would end up being 3 for the number of infrared bands that exist?
Because we have them together.
No. It's because this one, we actually have a degenerate band. Yeah, we have 2 degenerate bands, actually. Okay? Yeah. And so that's actually the degeneracy there. And so this, by the way, is that full character table, in case you're wondering. This is what links these two together. So if you were to take this, you were to solve for all of the different ways this moves and when it vibrates, this would be that. And then you can distill it down into a linear formula, which is this right here. Okay? Okay. So these are actually the vibrations. This was what you would have to do if you wanted to do it the way the book did. Okay? So you would actually have to take CO2, and these are all the different vibrations that can happen for CO2. And how do we know how many vibrations exist? 3n minus 5, right? Because it's linear. Okay. So 3 times the number of atoms, 3, then minus 5, right? Okay, so we have 4 vibrations. Now, we have the asymmetric stretch, we have the symmetric stretch. These are these ones right here. And can everybody see how those would work? Okay. If not, I actually have something to help you out. There we go. Okay. Oh my God. Can I actually mirror my man, these projectors are weird. Okay. Can I even see that? Alright, is it showing up for you guys? Okay. Alright, so this is actually the 2 bending vibrations. This is one of the bending vibrations right here. Okay. If we did it in the other direction, though, what would happen? Would it look any different? No, it doesn't look any different, does it? So that one's actually degenerate. Now, that spectroscopy table that I gave you actually takes into account for that and does that for you. And that's why you got 2 vibrations, is because it's actually degenerate right here. Mm-hmm.
And that was represented by the parenthesis x comma y.
Also by the symbols next to them, the U and G. Yeah. And then that right there is your symmetric stretch. And that's what your asymmetric stretch looks like. Okay. Everybody see those okay? All right. Fantastic. Okay. Can you guys still? No. Okay. Send that back out. It's like covering that up. Oh, that is just fantastic. All right. So again, these ones are the ones that are degenerate right here, okay? And they show up at the exact same spot. That's 600 something, which is one of the stronger bands, by the way. That's actually, if you look at them a little bit more succinctly, that is specifically the 1388 one. That's symmetric. That's only Raman visible. And that's because you have no change in dipole. Can you see your overall dipole would not change for the molecule? Can everybody see that? Okay, so the reason that the overall dipole wouldn't change is because they move directly equal, right? So the electronegative groups, which would be the negatively charged on both sides, are equaling each other out when it's the symmetric stretch. And so you have no overall dipole change. Okay. This one right here, you actually have an overall dipole change because one of them comes in, one of them goes out, right? And that's going to give you a different amount of negative charge on each side. And then these ones are the exact same as each other because the dang thing's linear, right? Okay. Okay. If it wasn't infinitely symmetric like this at infinite rotation, then these wouldn't be the same. But it is, so these are degenerate. Okay. So if you were to actually look at the spectra for this, what's that going to look like? Let's say we're looking at the infrared spectra. We're trying to figure out what's going to happen with global warming. It's carbon dioxide, right? Okay. How many places in that infrared spectra does this absorb in? These are degenerate, so it's just going to be 2. So there is 3 modes, but 2 of them are degenerate. Yeah. Okay. And so we'll see a band up at 2349-ish, and that'll be a fairly tall band. This one right here is going to be a medium band because it's the bend. Doesn't have as much absorptivity and as much intensity. And we'll just see a single band right there. Okay. Now, if we do have something that somehow makes this non-symmetric for whatever reason, because we have something binding to it, something's doing something to it, we could start seeing the 2 bands split. Okay. But it would require it to not be symmetric anymore somehow. Okay. Okay. And by the way, how effective is CO2 at absorbing infrared light and thus causing the greenhouse effect? Not that effective. Yeah. And that's because it only has 2 damn bands, right? Yeah. There's only 2 bands in the infrared. So.
What does water have?
So again, water is mostly not symmetric. It's low symmetry. So if we come up here 3n minus 6. How many atoms are there? 3. Yep. And so 3 times 3. Yeah. And so there's, yep, there's 3. Yeah. And they're all infrared active. Yeah. To a degree. There's several ones that are very infrared active. Remember the OH stretch? Very infrared active. Now the interesting thing about water is actually it has a lot of rotational as well, because it has fairly low symmetry, and so the bands are really broad too. Yeah. This doesn't have a lot of rotational because most of the rotation happens in modes that's not infrared active, right? So it doesn't have like any broadness due to rotation. And so you see real sharp bands. Yeah. The rotation just doesn't interact with the infrared much. You can get a little bit of it though, the C2, but that's it. Yeah, that's actually kind of an interesting thing about these. Yeah. So. Anybody have any questions? No. Okay. We're going to go ahead and move on to Chapter 7. You'll notice that Chapter 7, again, is a chapter where we take something that you kind of thought you knew in life, and then we expand off of it, right?